days in phylogenetics. Okay, so to begin my talk, I will start with this fact that us as evolutionary biologists and phylogeneticists love discussing about, talking over, lamenting over, and publishing on. And that is the fact that evolutionary processes can generate phylogenetic conflicts. Now here I have underlined phylogenetic to emphasize the fact that we know that evolution can both directly impact the genealogical history of a locus, as well as inferences that we may want to make off of that locus. And by now we have a number of documented sources of these phylogenetic conflicts. Of course, perhaps the most pervasive is incomplete lineage sorting, but we also have documented that gene flow, recombination, and even selection can impact phylogenetic inferences. So for example, here I have some work from my advisor, Todd Casteau, in 2009, in which they found that strong convergent selection at multiple amino acid sites within mitochondrial genomes of several squamates strongly misled phylogenetic inferences under our current phylogenetic models. For example, here we see that convergent molecular evolution basically moved this clade with 100% posterior support elsewhere in the tree. Okay, so with that sort of introduction to the basic idea of my talk, over the past decade, multi-species coalescent models have become an invaluable tool for estimating species trees, delineations, despite incomplete lineage sorting. Now, fundamental to all coalescent models, or at least most of them currently, is the assumption of neutral evolution. So this assumption allows us to model the genealogy and the mutations independently. What that really means is that the gene tree topology of a locus is not affected by its particular allelic state. Practically speaking, this also allows us to derive the probability distributions for a number of random variables such as the number of mutations, topologies, and so forth. For example, here I have a species tree, and below I have 3 competing gene tree topologies with their associated probabilities under neutral evolution within the species tree. Okay, so we realize that this assumption is a fundamental part of the model, is important to the model, but we don't know whether violating this assumption would have any real consequences. Now, in the literature, we see several conflicting opinions among different authors. For example, some authors say selection is probably not that big a deal. So here we have a quote from a recent Scott Edwards paper stating, "Selection often occurs at a minority of loci in the genome, in which case any spurious signals would likely be swamped out by the many neutral loci." Also, authors have stated that selection could, in fact, help phylogenetic inference. So here's another quote saying, "Selection could actually be a boon for phylogenetic analysis, making gene trees more congruent with their species tree." Now, regardless, multiple authors have stated that genes experiencing species-specific positive selection are not really appropriate for these methods. All right, so that brings us to the 3 main questions of my talk today. The first being, can positive selection influence coalescent inferences under the model? Secondarily, I'm interested to know whether selection could potentially help, hinder, or do both depending on the particular situation and scenario. For example, selection could help the model by increasing resolution of species delineations. Conversely, selection could hinder the model by increasing our confidence in a wrong species tree. And then finally, I'm interested in understanding and exploring what particular evolutionary scenarios and experimental conditions may be most susceptible to the effects of selection. For example, can the effects of selection have more influence and leeway when divergence time is short versus long? Additionally, I'm interested to know what happens as we sample more alleles per species within a species tree. Okay, so to take a stab at these questions, I simulated genealogies on a wide variety of scenarios of the 3-species model. Down here you see the 3-species model. A and B are sister taxa that diverged at tau AB. We have species C as the outgroup that diverged here at time APC. Now, to simulate a genealogy with selection for my models, I add a selection coefficient within species A for a positively favored genotype after it diverges from species B and their common ancestor. Okay, so additionally for my simulations, I use a theta of 0.01 for all species within the tree. I vary these 2 divergence times, and I'll explain a little bit more of that shortly. I also vary the number of loci, and today I'll show you the results for a single locus, 2 loci, and 10 locus data sets, both with and without selection. I also vary the strength of selection, the selection coefficients at the selected loci, ranging from 0.01 to 0.10 and 0.50 at a very high selection coefficient. Additionally, I use 2 different numbers for the alleles sampled per species, using either 5 or 10 alleles sampled. I repeat this process 500 times for each parameter combination using MSMS. I then estimate rooted species trees, species delineations, and parameters using BPP. Okay, so to give you a better idea of my simulation models, here we have 2 of the results shown today show 2 different divergence models. Over here to the left, we have a recent divergence model with a root height of 0.0001, and we have a more ancient model with a height of 0.001. Now, additionally, within these 2 divergence models, I vary the speciation time for A and B at either shallow in blue, as you see here, or more deep in red, with a deeper divergence time. Okay, so let's take a look at some of my results. So, perhaps the most interesting and I think exciting part of these and results of these simulations is the apparent effect of selection on gene tree distributions. Okay, so here I have the proportion of genealogies that are incompletely sorted in blue and completely sorted in green within species A. So immediately off the bat, you can see that there is some fairly dramatic effect of selection on these gene tree distributions within my species tree. In fact, even relatively weak to moderate selection can give us around 93% of genealogies that are completely sorted within species A. Additionally, across the board, you can see that strong to extremely strong selection coefficients can give us anywhere from around 92 to 93% to up to 98% of your genealogies that are sampled that are completely sorted within species A, which in my opinion is quite remarkable, especially when we compare it to the proportion of neutral evolution, which in these cases is around 2% within these very recently diverse models. Of course, things like this will change as we stretch out time within our species tree. Okay, so here I have the results for the single locus species delimitation analysis. On the left, I have the results for the recent speciation model. On the right, the more ancient model. Additionally, I've split these graphs up. On the left, I show you the 5 allele sample per species results. On the right, I show you 20 allele sample results. Here, the y-axis, I'm showing you the mean and standard deviation across those 500 replicates for the posterior probability of a species A existing. So this is our statistical confidence under the model that species A is a real genetically isolated taxon. Now, right off the bat, you can see, which is somewhat expected, that as we add stronger and stronger selection at the single locus, our posterior probability of species A increases, in some cases quite substantially. For example, here under neutral evolution, we have a posterior of around 40%. We had a very strong selection coefficient. This is a mean of around 90% posterior probability. Additionally, you can see that when we sample more alleles per species, for example here in the 20 alleles data, this result becomes more extreme and more pronounced, so that in many cases, under strong to very strong selection, we have a 100% posterior probability of a species A from only a single locus. Additionally, we see the same general trends of an increasing posterior probabilities as we increase divergence times here in the ancient model. However, we see somewhat less of extreme effects, particularly when divergence times are deep, because by then we have basically enough evidence to suggest that species A is a real entity. And so for the remainder of my talk, I'll be primarily focusing on the recent speciation model. Okay, so here I have the 2 loci and the 10 loci results shown on bottom. These graphs are organized in the same general manner. On the left, we have the 5 alleles sample results. On the right, we have the 20 alleles. Additionally, I partitioned these graphs to show you the differences among proportions of loci that are under selection. For example, here in yellow, we have a single locus out of the 2 that is under selection. In the orange, we have both loci under selection. Down below, I show you 2 out of 10, 5 out of 10, and then finally all 10 loci under selection. Okay, so as you can imagine, as we add more and more selected loci to the mix, guess what? We're going to get higher and higher posterior probabilities, even with relatively weak selection coefficients. Of course, this effect is most extreme when we take the most extreme amounts of loci, the numbers of loci under selection. And so we have many cases with 100% posterior probability of species A. Now this effect is further demonstrated when we look at the posterior probability of having 3 species over there on top, which is basically our statistical confidence that species A, B, and C are all genetically isolated taxa. We see even with a single locus, we add stronger selection, the posterior probability of having 3 species increases. Now conversely, when we look at the posterior probability of only a single species, shown here at the bottom, and this is a species that lumps together A, B, and C into a single taxa, decreases with even a single locus under strong to moderate selection. All right, so next I'm showing you the results for the single locus data sets for species tree estimation under the multi-species coalescent model. Now, this is a little bit more interesting trend we're seeing here. Even with relatively recent divergence times and lower allele sample per species, we're seeing a slight decrease in the true species model as we add stronger and stronger selection. This is further demonstrated here and even stronger as we bump it up to 20 allele sample over here on the right. We're under neutral evolution, the posterior probability of the true species tree. Let me rewind. So this is a posterior probability of the true species tree up there on the right. Up there on the top, this is the actual simulated model that we simulated these gene trees on, right? So we're seeing it decrease even with 20 allele sample per species. So in these cases, it actually goes below around 15 to 20% posterior probability as a mean across these replicates. Once again, we see the same general trends in the more ancient model. And here on the right, we see under neutral evolution, we see that we have a near 100% posterior probability of this true species tree up here. And then as we add stronger and stronger selection down below, this goes to around 70% posterior. Now, once again, you can imagine as we add more and more loci under selection, this effect becomes more pronounced. So that in the most extreme cases shown here, where we have multiple loci that are sampled under selection, in many cases, our posterior probability of the true species tree is beginning to approach 0%. Now, as you can imagine, as the posterior probability of the true species tree is declining, however, the posterior probability of this wrong species tree topology with B and C as sister and A as an outgroup is actually increasing, even if slightly. In this case, under very strong selection, we see a posterior of around 70% for this wrong species tree topology that's increasing. Now, once again, we add more selected loci to the mix with stronger selection coefficients. This effect becomes even more extreme and pronounced. For example, here, when we sample a total of 10 loci under selection, we have a mean of near 100% posterior probability of the wrong species tree, the wrong rooted species tree, under the coalescent model. This is further reflected with an increase up here, when we have only 2 loci that are selected. Okay, so in conclusions, to answer my question, I think it really depends on the particular evolutionary scenarios and experimental conditions on the effects of selection. For example, theoretically here, and I want to emphasize the word theoretically, extremely strong and extremely pervasive selection can potentially mislead species tree estimation under very specific conditions. And I think an equally important question is what are the potential empirical implications, and that really depends on the particular empirical system that people are using. In a lot of cases, questions like these are still left to be answered in the literature of how much of the genome is under selection. Additionally, we see that selection can be largely beneficial for species limitation. Conclusion, I'm expanding my simulations with more loci, different tree topologies, different types of selection, different population processes. I'm also interested in understanding these potential effects in empirical studies. So here, I've recently developed a Bayesian posterior predictive framework in R that we've used to identify potential targets of selection from genomic data and for further phylogenetic analysis. With that, I'd like to thank you today, and if you have, I think I might have a minute for questions. Thank you.